In this video, we are going to see different kinds of mathematical structures. They might be different at first glance, but at the end of this video, you'll find some shared properties that repeat in all of them. Our first example is a clock for which instead of 12, we have 0. If we add 2 steps to 1, we'll get 3. By adding 4 steps to 9, we'll get 1. By subtracting 3 steps from 1, we get 10. And we know subtraction can also be written as addition, so we can write it as 1 plus minus 3. And also, we can use one of the numbers on the clock to do so. By adding 9 to 1, we get the same result. Basically, for each element on the clock, there is an element called the inverse, that if we add them, we always get 0. This 0 is the neutral element. Also, by adding this neutral element to any element of this set, we will get the same element. This kind of addition is called modular addition. For example, we know that 8 plus 7 is 15, but modular addition has to do with the remainders. The remainder of 15 divided by 12 is 3. It doesn't matter whether we add 2 to 11 and then add 3, or first add 3 to 2 and then add 11. The outcome is the same. Pay attention that in this example, instead of adding 11, I have used its inverse and subtracted, which has the same effect. We have a similar structure with angles. If we add 90 degrees to 300 degrees, the result is 390, which is 30 on the circle. In this case, instead of discrete values, we are dealing with continuous ones, which are angles. So we have a set of all the angles. And this operation means addition takes each element to another angle which is in the same set. Also, there is a neutral element that doesn't change the point on the circle or the angle on the circle. For each element, there is an inverse, and we will get the same result for both of these expressions. Now, you might be thinking of another structure you have seen before. All the integers, and the operation we want to investigate is again addition. Pay attention that this is just a set that contains all the integers as elements. But this one is a set, and there is also an operation that can operate on all the elements of this set. If you add 2 elements of this set, you will get another element which is in the same set. 0 is the neutral element, and if you add it to any integer, it doesn't change it. Also, for every element of this set, there is an element that if you add, the result is the neutral element. This is the inverse. For every positive integer, the inverse is the corresponding negative integer and vice versa. And again, for this operation, I mean addition, it doesn't matter which of these I use. Both give the same result. These are the names for these properties. So from now on, for the first property, I'll say the set is closed under the operation we are talking about, and it is associative as the last property suggests. Let's take a look at this geometry example. When this operator E acts on this square, nothing changes, and it gives us the same square without any changes. But this one, A, rotates the square 90 degrees counterclockwise. Operator B rotates the square by 180 degrees counterclockwise, and this last one does a 270 degree rotation. So this is the set of operators we want to check the 4 properties for. The combination of every element with E gives the same element. So E is the identity element. For each element, there is an element in the set that when combined gives the identity element. So every element has an inverse. Also, the combination of every element with other elements in the set gives another element in the same set. I have just mentioned some of them. This is the closure property. And finally, this operation is associative. Now, it's time I gave you the definition of a group. To define a group, we need a set and an operation. This operation, or group law, takes 2 elements from set A and gives another element in the same set. If we call these 2 elements A and B, the combination of A and B under the defined operation is again in the set A and is shown by A asterisk B. These are the 4 examples we talked about. Take a look at them and try to make sense of the set they represent and also the operation that maps each element to another element in the set. Pay attention that I use the word map. This is the definition of a map from one set to another. In this case, a map that assigns to every pair A and B an element of the set on the right, which is again A. Also, there are 4 group axioms that must be satisfied: closure, associativity, existence of a neutral element, and an inverse element for every element in the set. Closure suggests that the result of the operation is in the set. This is associativity and is difficult to be said in words. The third axiom suggests that there exists an element in the set such that for every element A in the set, this equation holds. And finally, the last one suggests that for every element in the set, there exists another element in the same set for which the result of operation is the neutral element. Finally, the groups can be commutative or non-commutative. If they are commutative, they are called abelian groups, and otherwise non-abelian groups. All the examples in this video were abelian groups. In the next video, we are going to see more examples of groups which are also non-abelian.